let's get started. And so first thing, for people who have questions during the talk, feel free to put them in Q&A, and Lia will answer either along the way or at the end of the talk. All right, so welcome everyone. Oh, by the way, I'm Jing Liu, MIDAS Managing Director. So before I introduce today's speaker, I want to mention a couple of housekeeping items. So the next two speakers, next week we'll have Enrico Dominin on the economics of biodiversity conservation. And then there's 1 week break. Afterwards, we have Virginia Dignam on responsible AI from principles to action. I want to also thank our sponsors for the seminar series: American Mathematical Society, China Scope, Microsoft, Rocket Companies, General Dynamics, and Yazaki. Okay, so today we're really happy to have Dr. Lia Corrales as our speaker. Lia is a faculty member in astronomy right here at the University of Michigan, and she leads the Space Particulates in Complex Environments Research Group. She uses high-resolution X-ray spectroscopy, imaging, and dynamic modeling, among other methods, to study the transitions between solid and gas phase materials in unique environments, from the interstellar medium to exoplanet atmospheres. Lia received her PhD degree in astronomy from Columbia University. Before she took her current faculty position, she was also an LSA Collegiate Fellow. In addition to her research, Lia is also passionate about promoting equity and inclusion in the research community. Most notably, she founded and runs the Women of Color Coders, which is a peer network group, a peer mentoring network for women of color researchers, especially in the open source software community. So her talk today, as you can see here, is how I learned to stop worrying about low signal to noise data and love statistics. So I think the next hour will be really fun. Again, audience members can put your questions in Q&A at any time. So with that, Lia, I'll let you take over.
Thank you for the introduction. I'll work on sharing my slides. There we go. All right, so thank you. I'm very excited to be here today and talk about both my science and my data. I added a subtitle to this talk, sorry, called The Power of Forward Modeling, because I realized that a lot of the love of statistics also came from this love of this particular technique that we use a lot in high energy astrophysics. So I just want to point out that I have specific goals for this talk. In particular, I want to showcase the unique data analysis techniques applied to high energy observations of our universe. I want to spotlight areas of astronomy where new approaches to data are really revolutionizing the field. So I'll talk about not just stuff I'm trying to do, but stuff I want to do. And in general, I'm really open and interested in collaborating with people on some of these techniques, because a lot of times there's just a lot of software or a lot of nitty-gritty that needs to be done that we don't always have time for when we're trying to write proposals and do other science. And so this is an area that's really ripe for collaboration. So first off, I want to introduce my group. As Jing mentioned, I named it Space Particulates and Complex Environments because one of the unifying factors is really trying to understand dust and other particulates in an astrophysical context. So I've identified 3 major research areas for my group, and I'm highlighting here my 2 postdocs, Iona Sadaraki and George King, who work in various aspects of this. So kind of my bread and butter, what I worked on for my PhD is X-ray observations of dust in the interstellar medium. And in particular, we're interested in astromineralogy, which is understanding the composition, so the actual mineral structures of dust grains in the ISM, as well as the sizes of the particles. And I'm on the science team for CRISM, which I'll talk about a little bit. where we hope to do a lot of work there. I'm also studying exoplanets, and in particular exoplanet transits in the near UV. I'll talk more about that science in a bit. And my postdoc, George King, is an expert on characterizing stellar hosts of exoplanets in the X-ray and the UV, as well as measuring high energy transits. And finally, I'll showcase, in particular in this talk, work that I did in a previous postdoc to understand our local supermassive black hole in the galactic center. And you actually see an X-ray image up there, and you'll see more of this image in a bit. And this is something that I have been searching for a graduate student to work on, and I'm hoping to kind of shepherd them into being the next expert on this particular field. Okay, the first thing I want to do is give you an overview of X-ray astronomy in general to kind of get you familiar with the kind of things that we're working with. Oops, there we go. So this spectacular image is actually fairly recent. It's from a telescope called eROSITA, and eROSITA is an all-sky survey in the X-ray. So this is the entire sky. And it was launched by, well, it's a joint effort by the German and Russian governments to put a new X-ray telescope in space to get this entire map. It covers 0.3 to 2.3 keV in terms of the energy range, which is actually quite soft for most X-ray astronomers. And in this particular projection, they're showing the night sky centered on the Milky Way. So what you see here is the plane of the Milky Way. So this is the disk where most of the stars are in our galaxy, and it's got a lot of dust, which is why you see kind of like the wispy, dark structures. But in general, the other stuff that you see in the X-ray is diffuse millions of degree gas. And a lot of the gas that you see here in like the red and the kind of yellowish, so that's super hot gas that's filling the space around our galaxy. So that image in the upper right is an artist's conception of what, you know, a puffy ball of gas around our galaxy might look like. We also have point sources, and the one that I'm pointing to in particular is called Cygnus X2, and it consists of a low mass star where some of its material is falling onto a compact object like a neutron star or a black hole, and as it falls into the compact object, it heats up to millions of degrees and emits in the X-ray. And finally, we also have plenty of hot bubbles of gas in the interstellar medium. So the one I'm pointing to in particular is a supernova remnant. So this is the remnant of a star that exploded and just heated up everything around it and created a cavity. So these are examples of the kinds of things that we're looking at in the X-ray. And there's just a myriad of science to be done. The science I'll be focusing in on particular, the way I describe the data that I'm using is really tailored for the instruments that are on board the Chandra X-ray Observatory. And I'm such a huge fan of Chandra. I can go on and on about why it's amazing, but I'll just tell you in one slide all of the best facts. So the Chandra X-ray Observatory was named after a physics Nobel Prize winner, Subramanian Chandrasekhar. He's a very famous physicist. He worked on things like compact objects, stellar structure, fluid dynamics, and he was just such an amazing person. And so they decided, because he was very important in the field of compact objects and astrophysics in general, that they would name this X-ray observatory after him. It was launched in 1999, so it's been in space for over 20 years on the space shuttle mission 93, which also was the first space shuttle mission that had a woman commander, and that was Eileen Collins. So it was a really great milestone in NASA history. And another fun milestone is that also this telescope is the largest payload ever put into space by a space shuttle mission. So it was a pretty big deal. And in particular as well, Chandra has the best X-ray imaging technology available and will remain unsurpassed for at least several decades. So this is the best imaging resolution we could possibly get in the X-ray. And we can now make lighter, less expensive, and similar mirrors, but they're not able to surpass what Chandra has been able to do. And finally, one of the great things about Chandra is that it has no expendables, a stable orbit, and incredible longevity. So as long as NASA wants to keep supporting it and things continue to work as they have been working, it can literally go on for decades. So it's a really incredible telescope. Like I said, I'm such a big fan. I just wanted to advertise all the reasons why I think it's the best telescope in space. So I just want to give you a quick overview of how we treat X-ray data. And the Chandra has a variety of instruments, but the ones that I use the most utilize a technology called CCDs, or charged coupled devices. And it's basically the same stuff that's in your phone. So on the left here, bottom left, you see like an image of a CCD array. And quite often what we do is you make many CCD chips and you put them together. We'll see an example of what that looks like in astronomical imaging. But it's a pretty straightforward concept. Basically what happens, because our collecting area on our telescopes is actually relatively low, we can count individual photons. So when an X-ray photon comes and interacts with our charged coupled device, it hits the material and that energy gets deposited in a way that liberates electrons from the material. And then those electrons, which have been slightly liberated, are still trapped within a certain area of the detector. And so each pixel on the CCD traps a bunch of electrons. Now, based on the energy of that particular photon, you can basically translate, if it has a higher energy, it should kick out more electrons. If it has a lower energy, you have slightly fewer electrons. So you can take your signal from your charged coupled device and translate it to the photon energy that you expected came from that photon. Now, in theory, this is a one-to-one transformation. Number of electrons or signal out, total energy of photon that you absorbed. However, there are lots of complicated things about materials and their interactions with X-rays that makes it not ideal. So I've drawn here a little graph of what I like to think of as like a probability distribution function. So if you have like an X-ray that interacts with your detector, in theory, marked by the dotted line, the photon energy you can back out by taking the number of electrons or the signal that you see and multiplying that by whatever energy it requires to liberate those electrons. But there's always a little bit of a tail, and there's things like special absorption that can create something that's not exactly one-to-one. So in that sense, we're going to have to think more carefully about our data. And the last thing I want to point out is by using this like photon counting kind of mode, we have very, very rich data sets that give us both position on the sky, that X and Y, the energy, and as well as time. So there's a joke in X-ray astronomy where basically X-ray astronomers give every photon a name because we really are working with small number counts. So we're counting individual photons, and then we have to deal with the fact that it's not a one-to-one transformation between signal and energy. So this image right here shows what a response matrix looks like. And this is basically how we deal with translating our incoming or true energy, which is on the x-axis, to how our detector perceives that energy, which is on the y-axis. So the way I like to think about these particular matrices is if I drew a line, a vertical line in this case, I basically have in there a cross section of the probability distribution function at that particular energy, because each energy will cause different types of effects in the detector. And I like to think of like X-ray astronomers as like the Ford prefect of astronomy, because when we're presented with all this complexity, we don't panic. We say, it's all right, we understand our detector. What we're gonna do is we're just gonna forward model the heck out of it. So basically what we do is we take our response, and I've shown it here as an integral, where as long as we have a spectral model marked with S and our response matrix, we can say, okay, this is what my model looks like. Let's apply the response. integrate, multiply by exposure time, and all I have to do is duplicate what my observed count histogram. So that's basically the H there represents like the perceived energy that the detector is telling you it got a count at, and we can compare things. So it's pretty straightforward. You take your model spectrum, you'll have, a bunch of parameters, which I've just written as phi here. So the spectrum is basically how bright is the thing I'm looking at as a function of energy, given some special parameters. I do the integral to apply my response. I get out a model counts histogram. I compare that to my observed counts. And I do that when I compare them, I have to pick a statistic to decide how good is this model. For X-ray astronomy, because we're using counts information, we use Poisson statistics, which gives us what's called a cache statistic. That's the name of the particular thing that we use to judge goodness of fit. We ask ourselves, is it a good fit? Are we happy? If the answer is yes, we report that. If the answer is no, we can go iterate those model parameters, go back to the start and do it all over again. So in this way, we can search parameter space for the best fit model. I tend to prefer NCNC methodology, but it's pretty straightforward and it's, we don't panic, it works. And the thing that's strange is that X-ray astronomers are actually quite unique in doing this among other fields of observational astronomy. So I just want to showcase as well a way that we can do even better, and that's with high resolution spectroscopy. So this is an image of Chandra being assembled, and on the left side bottom is where the telescope mirrors would be. So on the upper left, I'm showing the actual mirrors. They help focus the X-rays down to the other end of the tube. That's at the top right. Oh, yeah, I don't remember. Okay, so anyways, so there's also this piece, which you see on the lower right, which are little gratings. So each of those little squares that you see, it's like a cap that goes over the top and basically is aligned with each of those mirrors. And they're kind of like spectrum glasses. So if you've ever looked through like those rainbow prism glasses, it's like that, but for X-ray. So anytime we want to, we can tell a telescope to put these gratings or these rainbow glasses in the path of the mirrors, and we can disperse the light to get a spectrum. So this is a false color image, but basically what it's showing, there's two different sets of gratings and they each disperse light in a different direction. So we get this X pattern. And the way it works is that the longer wavelength light goes out and the shorter wavelength goes in, so increasing energy towards the center. But essentially, we can look at this, and then from this dispersed light spectrum, we can get an actual high resolution spectrum that's much better than our CCDs. So there's a really unique way to do this, because we literally are dispersing the light and then collecting it with the CCD. So we have the same type of information. We have spatial information, we have a rough sense of energy that comes from the signal or the number of electrons that were kicked out. And with that piece of information, we can sort each of the photon counts, which we call events, into a high resolution energy bin. So this plot on the upper left shows what the light looks like in the coordinates of that dispersed spectrum. So basically all I've done is taken this X and reprojected everything so that we're centered along the dispersion axis. So the X-axis is the dispersion direction, where the position along the X-axis is a function of wavelength. And then the Y-axis is the cross dispersion direction. So just perpendicular to that. And so we ask ourselves, does the photon position match the energy received by the CCD? So in other words, is it the right energy for this particular wavelength? If the answer is yes, we assign the photon count to that bit. If the answer is no, we can discard it. So what that actually looks like is on the lower left. So again, the x-axis corresponds to where the photon hit along the dispersion direction, which we can translate to wavelength. And then the y-axis is the CCD recorded energy. And you see these arcing patterns because essentially, if it matches, so shorter wavelength, higher energy, that's why it arcs up in the middle. And you can literally just draw a region and say, hey, events in this region belong to this spectrum. And we're going to build a count histogram to much higher resolution than was possible before. And so don't worry too much about the numbers, but the way gratings work, you get like multiple angles that you can like disperse your light onto. So that's what and then you have like a right direction, which is +1, and a left direction, which is -1. And that's what the ends mean, but you don't have to worry too much about that. It's really just, hey, look, we can pick out all of this information just by mapping it onto this new space. So this gives us an incredibly low background, and it makes it so that essentially our high energy spectral information, you can almost literally ignore the background until recently. So this is a project that I worked on as a postdoc when I was at MIT, and I was working with the Galactic Center, and in particular, Sgr. So Sgr is the name for the point source that corresponds to our supermassive black hole at the center of our galaxy. This image on the right is actually a radio image that was recently released by a South African radio array called Meerkat. And I just think it's a spectacular image, and there's magnetic fields and other weird stuff happening, but our supermassive black hole is somewhere near the middle of that bright source that you see on the lower right. So this is the X-ray image of the Galactic Center with Chandra, with the best imaging resolution possible, and the best imaging resolution we're going to see for decades. I just want to reemphasize that. Chandra is so amazing. So it's a total mess. And I'll just say there's a supernova remnant. That's the like orangey weird stuff that kind of looks like a stomach. That's actually a supernova remnant. All of the diffuse light you see is diffuse hot gas, a little bit in the foreground and a little bit in the galactic center. All of the points you see are those compact objects that I was talking about. And then we have a few like cometary structures that are like really unique types of objects called pulsar wind nebulae. So where is Sgr? So within that circle in black, I've highlighted, that is the central parsec. So like basically the central 3 light years of our galaxy. And Sgr is what you see in the middle of the gray box. And there's the famous image. I love this video. Let me play it again. Yeah, so a recent Nobel Prize went to Andrea Ghez of the UCLA Galactic Center group, and they worked on monitoring stars that went around this object. And so essentially they were able to measure the mass of the supermassive black hole that way. So all of those stars that you see in the animation are actually within this region that you see in the central parsec. And we don't see these stars in the X-ray, they're not bright enough. All we see is hot gas and some other compact objects. So why do we study Sgr? Basically, given the environment that it's sitting in, we expect the supermassive black hole to be 100,000 times brighter under standard models. So basically, this is our way to test our understanding of physics in extreme environments, because it's actually, for a black hole, not doing a whole lot. And so because of Chandra's amazing imaging resolution, we're actually able to map the temperature and density of the gas around Sgr as it's falling into the black hole. We're able to resolve that. So I was hired to work on this Chandra X-ray visionary project. So these are a series of projects that Chandra gave time to in order to do really big question things. So on the left, or on both images actually, so these are from 2 different campaigns. The one on the left is about 11.5 days of exposure, but it has only imaging information. The one on the right is what was obtained by the X-ray Visionary Project. So they had literally a 35-day exposure. So that's a month of staring at the galactic center. And in this case, we had the gratings in place. And so you can't see it because the image is so diffuse, but we've put rainbow glasses over the galactic center, and essentially the entire image has been smeared out across all of those different chips. So these are raw images, and you can see that the CCDs actually have slightly different sensitivities and backgrounds and things like that when you stack them up, and that's why you get that, you know, square blocky structure. So I haven't corrected for exposure or anything like that in these particular images. So my job was to look at the image on the right and extract a high energy spectrum, which looks, you don't see the X because Sagittarius star is so dim. So I will just briefly mention some of the things I had to do. I said that because of the order sorting algorithms that we use, you normally can ignore background from our high resolution gratings information. So that is definitely not the case with Sagittarius star because it's not the brightest thing around. There are plenty of things that are just as bright nearby, such as this kind of cometary structure next to it. And so when we take our different background regions that are just next to Sagittarius star, we start to see echoes of that cometary structure. And so I had to like aggressively filter for that, which was definitely non-standard. We also did things like filter out point sources because there's point sources all over the galactic center. And we've dispersed or spread out the spectrum of Sagittarius star, but there's still images of point sources in the way. So here you see just some point sources. Some of them kind of overlap with the central image. Some of them overlap slightly with the background. And what that does is that it could artificially inject, right? Just because you have something sitting in the source spectrum, let's say, and when I do my order sorting, there's a random point source there. What it would do is artificially, accidentally give you, let's say, a perceived emission feature just because it happens to line up with the 3 angstrom region of the dispersed spectrum. So we did a bunch of aggressive filtering for that. So this is a plot from my paper, and basically what we did is, like I said, we're taking count histograms, and that's what you see in the top panels. So these are just 2 different types of gratings, and these were the best looking spectra we had in terms of signal to noise, but you can see that the background is still the majority of it. So the background spectrum itself is shown in that dark blue. And then what I did is I just took a spline of the background because there's no physicalness to the background. It's all just diffuse plasma and background and random stuff. So we fit a spline to the binned data, and that's what you see my forward modeled spectrum in the light blue. And then the foreground, or like the source spectrum, is shown in black. And so of course that's the background plus whatever Sagittarius star is doing. So we fit a really basic model to it, and that's what you show in red. So this is a power law and a Gaussian. And the top is really just what that power law and Gaussian looks like in count space. And in the middle, I show the residuals that are just the counts histogram with of just the source. And then the bottom, you see residuals between the model and the actual source information. One thing I did is I evaluated things separately, and I said, because we want to make sure that we don't have any extra features that aren't real, so we need to look for something that exists in both. And so that's when I found this little feature at about 4 angstroms. But this is basically the best we can do right now with Sagittarius star. And one thing in particular is that we have a lot of debates in X-ray astronomy as to whether or not you should bin data. And so all of this was fitted in unbinned space, or fit in some, like the background was fit in bin space, but then like projected to unbinned space in order to basically get an appropriate model of the background, because to be honest, it's a lot of zeros and ones. So it's quite complicated. One thing that I've been kind of bothered by is that I'm not able to fit, like the background model is fixed. I'm not able to kind of fit the background or let it wiggle a little bit with the source spectrum. And that's something that I'd love to work on someone if they're ever interested in it. So what did we learn? So we can fit some of the features in the spectrum with a Gaussian and get some information out. And it turns out it's not any better than the CCD, which is much lower resolution by about a factor of 50. So we can look more closely at the spectrum in unbinned space. And when we do that, here on the left, I'm showing the count histogram again, but I've unbinned it. And the red curve shows the best fit model that was done to the CCD spectrum that was lower resolution, but then, you know, again, projected it into a higher resolution space. And it roughly agrees, but there are plenty of features that actually have kind of a higher looking confidence than what you see in the 1.82 to 1.86 angstroms range. And it's just looking like things aren't really adding up. And part of that is because with the spectrum, because we've dispersed it, but there's nothing blocking the rest of the light, we're actually probing like this extended, what I've labeled in this blue ellipse, like we're probing an extended region of the object. And the actual image that we're looking at in terms of like what we're picking up from the order sorting algorithm is also a function of energy. So it's quite complex. And what we're going to need to do is forward model it. So the next steps that we're planning on taking is really just looking at hydrodynamical simulations and projecting them onto or folding them through the entire instrument response in order to say, hey, we have these concrete predictions about what the gas around Sagittarius stars should be doing. All we have to do is deal with the instrumental effects. So up here, I'm showing some images from hydrodynamical simulations from Calderon et al. And what they've done is they've noticed that there are two different ways that this particular black hole could be accreting. There's like a disk mode where it forms a disk, and then there's like a puffy mode where it's like mostly spherical. So we should be able to test these by modeling it and then folding it through the response. So what I'll talk about next is why that's been a bigger deal than it seems like it should be, and also where we're going. So really, it's an exciting time to be an X-ray astronomer because there's some really cool new technology coming to light. So in particular, I'm one of the scientists helping lead the science case for XRISM, which is the X-ray imaging and spectroscopy mission. This is a telescope that's a joint effort between the US and Japan. And the goal is to put a microcalorimeter in space. So a microcalorimeter, much like a CCD, is a photon counter. But instead of kicking out electrons and using that, what it's doing is it's just an incredibly sensitive temperature device. So an X-ray photon comes in, it hits a pixel, it heats it up, and that changes the signal, and you can get the energy from the photon from that. So this plot on the right shows like the CCD spectrum, the low resolution, versus what we're going to get with microcalorimeters. Now, unfortunately, with XRISM, it has very poor imaging resolution. So the European Space Agency is developing an X-ray mission called Athena that will be launched in early 2030, or the 2030s, really. So XRISM is a detector that's basically 6 by 6 pixels and about just very low resolution. So here's an example of what like a galaxy cluster would look like with XRISM versus with Athena. So this is also like next stuff. But the whole point is that basically we're going to have a very high resolution spectrum for every single pixel in these images. So essentially we're looking at a spectral cube. So in general, in the X-ray community, we can forward model a lot of things. But in general, the norm is that images and spectra are treated completely independently. So here's kind of a cute example. I really like this work. So this is, again, Sgr A, the supermassive black hole. What they've done is predicted how the gas should be distributed around the black hole. And so the top panel is the theoretical model. The middle panel is the predicted image, and then the bottom panel is the residuals. So again, this is just an imaging space though. And there is a bit of spectral information. So on the left, you've basically collapsed all of the energy down to 1 to 4 keV, and in the middle, it's 4 to 5.5, and on the right, it's 5.5 to 9. So a lot of the spectral information has been compressed down to a lower dimensionality. But like I mentioned, like we're going into a place where we're going to have a super high resolution spectrum for every single pixel. And this isn't really that new because X-ray imaging data sets have always been spectral cubes. They just haven't really been treated as such. So here's an example. This is a really famous X-ray image from Chandra, and it's the Cas A supernova remnant. So this is the remnant of an exploded star. And, you know, the colors are created, it's a false color image, to kind of roughly map what energy they're at. So bluer is higher energy, et cetera, et cetera. But when we want to extract some science information spectrally, what we tend to do as X-ray astronomers is plop down a few regions and extract a spectrum from it. And in theory, we can model all of the spectra together, and we can tie together the model parameters if we have some spatial information. But we're really starting to get limited because these spectral cubes are going to get very, very big. And what we need in order for those to happen is a little bit more information than we've had in the past. So here I'm just showing some of my science, which is studying dust echoes in the interstellar medium. And on the left, you see a real image from Chandra. In the middle, you see how I can actually simulate that scattering halo. There's some things like I can't really simulate at this point the patchiness of dust coverage. But you have a relatively lower signal to noise image. And then on the right, I have a simulated what this scattering halo would look like with another concept mission for a telescope. But the thing that's missing from all of these is that I don't have a sensitivity map as a function of energy for my CCD. And I haven't been able to map the response, so energy in to energy perceived on a pixel by pixel level. And in addition, I'm missing some X-ray background. So these are like the types of tools that we need to fully forward model our spectral cubes, because what I really want to be doing is forward modeling in a 3D counts space. Why do we want to do this? This is just a quick example showing how we can differentiate between different minerals. And this is something we plan to do with PRISM in some way. And I'm not going to get into the nitty-gritty of this flowchart, so sorry to like bombard you with information. But essentially, we're going to be doing 2 different pointings and tying a lot of information together. But when you see these simulated images, you can see that I can simulate a lot of information, but the fitting infrastructure isn't necessarily there. So there's still a lot of things. There's still a lot of work to do on that. So I'm going to pause and summarize what we've been doing. I just want to point out that X-ray data sets are a treasure trove of information because they contain photon interactions, which we call events. These interactions are collected in position, energy, and time. We have complicated instrumental effects to keep track of. So we vastly prefer forward modeling in all of our analyses, and handling instrument systematics doesn't scare us so much. But in general, X-ray spectra and images are always handled separately. So we're kind of reducing spectral complexity or reducing image complexity. So I really want to emphasize that our opportunities are being missed if we don't use the spectral and spatial dimensions together and fully forward model everything. And this issue has become a lot more apparent as the next generation of X-ray telescopes are increasing the spectral resolution of our imaging data sets by a factor on the order of 50. So there's a lot of work to do that I'm really excited about. So I said I wanted to pause and just answer any quick questions now before I move on to the next portion of the talk. I can also, I don't know, I don't hear anything.
Yeah, I don't see any questions coming in right now. So
Okay.
Yeah, you can move on, but just a reminder, people can put questions in the Q&A anytime.
I know it's a lot of information and it's a lot of like stuff that's, the science is outside of most people's general wheelhouse. Go ahead.
Yeah, wait a second. I think Jeff Fessler just put a question in chat. Is the spectral response different for every pixel?
Yes, the spectral response can be different for every pixel. And in particular, we can have pixel to pixel interactions called crosstalk. I'm not as familiar with like the technical details as to why that happens, but you could even tie those together if you wanted to. Great, I'll go ahead and move on because I'm really excited about this new information, which is where my research is going lately. So lately I'm working on characterizing exoplanet atmospheres at shorter wavelengths. And at University of Michigan, we have special access to a telescope called SWIFT. So SWIFT is a really fast telescope that was designed to study really, really high energy outbursts from very distant objects. But it's a multi-wavelength instrument. It can get gamma rays, X-rays, as well as UV and optical light. So with exoplanets, the UV is, you know, the longer wavelength stuff is slightly more relevant. So I decided to use the NUV instrumentation on SWIFT in order to characterize exoplanet atmospheres. So just a quick point as to why we would do this. This is a figure that I took from the Habax and Louvois white paper. So this is essentially like a science case for next generation telescopes to study exoplanet atmospheres. And so in this particular example, you can see that at short wavelengths, you can differentiate between an Archean Earth or a very ancient Earth that was just, you know, barely starting to develop life compared to modern day Earth. You can see there's quite a lot of variation as to what's going on in the UV, depending on the chemical composition, as well as what these things called hazes, which are particles that form in the upper atmosphere. Basically, I want to look in the UV to understand how we might be able to characterize hazes or other chemical reactions in exoplanet atmospheres, because there's a lot happening in that wavelength space. So I was not the first person to use SWIFT to study exoplanets. What I'm looking for are exoplanet transits. And what that means is when you have a star and a planet orbiting it, if the planet just happens to be oriented so that it passes in front of the star from the perspective of Earth, it produces a dip in the brightness of the star as you monitor it with time. So this was the first planet measured with SWIFT. It was WASP 121b. It's an ultra hot Jupiter, meaning it's about the size of Jupiter and it's super duper close to its host star. It's like within the orbit of Mercury for our sun, if you can imagine if there was a Jupiter-sized planet there. So this NUV transit was measured to be like 30% deeper than the optical transit. And what that was telling us is that there's an extra source of an absorption. And this particular group interpreted it as pieces of the atmosphere or diffuse gas from the atmosphere that was actually being stripped from the planet. So we went and we tried to get more NUV transits with SWIFT. So I'm showing here the best one that I have, which is disappointingly low signal to noise. But let me explain what I did. So SWIFT is a telescope that was not designed to study exoplanets. And if you want to study exoplanets, you need something with precision that's definitely less than 1%, often more on the level of 0.1% or less. So you need extremely high precision. And so when you have a telescope that wasn't designed for that precision, you don't have like photometric or basically like measuring standards that get you that. So here I'm showing on the left the raw light curve in gray. So this is like all of the UV data binned to about 1 minute per bin. And you can see that all of my data points have quite a huge spread on the order of like 10%. Now, that's really scary because I want to get something less. But in general, when I view this ensemble of data points and I fit them with a transit model, in other words, when I fit them with a dip in the star's light, I can actually get something that looks like a transit. So I've binned the light curve just for visual purposes. So we're fitting the gray data points, but I've binned it visually in the black. And what that shows me is that even though there's quite a lot of spread, the general trend of the data is to go down and then come back up. So that looks like a transit. On the right, I'm showing the parameter space that I fit. So the y-axis is the ratio of the planet radius to the star radius. So you just square that and that gives you the transit depth. So it's just the geometrical size of the planet that I fit. And then the middle is, or sorry, the x-axis is the transit offset from what I expected, because we're able to monitor these objects and say, okay, it should be, the planet should be transiting at X time. And I just kind of let that be a free parameter in the fit. So I do get something that fits. On the upper right, I'm showing contours of my best fit MCMC chains. These are 1 and 2 sigma contours that tell me that the planet actually appears quite large in the UV. And the next thing I did, which is what I call the brute force method, is I did null hypothesis testing. So these are the best fits to 10 to the 5 simulated transit light curves with no transit, so just light curves with no transit, based on the statistical properties of the actual data set. And you can see that those contours are offset. And when I do a calculation to see what are the chances of getting my actual best fit if there was no transit, it's less than 0.1%. So this is about a 3 sigma transit, and it's particularly deep and particularly weird. However, there's one big assumption that I've made, which is that all of these data points are independent of each other. They're not correlated. That's a pretty big assumption that could likely be wrong. So one way to kind of what I'm calling the next level is this technique called pixel level decorrelation. Just for the sake of time, I'll get to the main points. Essentially what you can do is take a grid of pixels that your source is sitting on, and you treat each pixel light curve independently. You literally forward model the light curve of every single pixel. So you have a model light curve, which is your science. You have the sum of your pixel light curve, which is kind of like your response. And then that helps you predict an observed light curve. So often we use a linear pixel model. So you would just say each of these pixel light curves can be approximated with a line, and then you have to define your physical model. This, like I said, 2-parameter transit model, which is the depth and when it happens. And just like our X-ray data, all we're going to do is take our model light curve. We're going to say, okay, given this model light curve, we're going to solve for our pixel coefficients, or the slope of the line, in a completely analytic way. It's just a 1-step process. So it's kind of like applying a response, except you're like solving for your response on the fly each time you do this. That gives you a predicted light curve You combine that with your observed light curve, compare it to your fit statistic. Are you happy? Yes or no? If you're not, you reiterate. So you can do this many, many times until you get the best fit. So this is something that we're planning on trying out with Swift or XMM Newton. And here I'm just showing a time lapse of some transit data that we have for this star called WASP-80. And you can see that it kind of dances all over the sky because actually our telescopes aren't quite as stable in the X-ray as they are with some other cases where this has been applied. So we're probably going to have to go to some higher order effects. But I'll stop here on my summary to just say that we're really excited about applying these new techniques to, again, telescopes that weren't designed to study exoplanets to really hammer down the precision and say whether or not we truly are seeing these deeper transits. So thank you for your time. I know we're close to the end and I'll take any questions.
Okay, so while we're waiting for other questions, let me start. I don't know anything about astronomy, so but one thing that you said when you were looking at your spectral analysis and so forth reminded me something of the sparse data problem that a lot of researchers in other domains have actually also been sort of grappling with. Mm-hmm. So I'm just wondering whether that could be, whether you've thought about maybe talking with, like biologists even, right? So, who study, really who encounter the sparse data issue all the time and see whether methodologically, whether there's any interesting way to learn from each other's approaches.
Yeah, I don't know as much about what specific approaches they use. Is that something to do with you might be working with small numbers of, let's say, people or?
Well, for example, one thing that people do a lot these days, when they study gene expression, especially at the low expression level, there are lots of zero counts. So, some are really just inaccuracy, right? And so, yeah.
Yeah, definitely. I would be interested to hear from that. And I mean, spectral cubes are something that are used in many, many disciplines. And one of the unique things, for instance, is just that if we had a lot of signal, we could ignore a lot of aspects of the response because they would be so tiny, because our signal is so high. And then we can just treat it as like, we know the flux as a function of energy. We know what the true thing should look like, which is what most other wavelengths do. But because our data is so sparse, we have to be really careful to say whether or not that photon is a real photon or something else, for sure.
Yeah, exactly. Yeah.
I see a question. Is EXO-3b an unusually large planet? You're not misinterpreting that. So that particular planet transit that I showed is 2 times, it appears 2 times bigger in the UV than it does in the optical, which is the biggest. It's quite a lot. So there are a number of explanations that we could explore for that. But it's definitely big. For reference though, people have seen 50% from planets that are like outgassing like crazy. So it can get large due to outgassing, for instance. I know it was a lot. I'm really sorry about that to bombard you with information. But yeah, there are a lot of exciting things to do. And one thing that I didn't mention was that there is some interest, although it hasn't quite been reached the mainstream, for using things like machine learning to, for instance, disentangle different sources and spectral cube data. But it's still there. It's like kind of connecting them to the physical models can be quite difficult.
Yeah, I'm not sure unmuting is a possibility, just for the audience members to know, but you can type the question or maybe raise your hand. So. Okay. So, yeah, so we're almost at time. So if we don't see any questions, we'll just I would just thank Lia for a wonderful talk. So we'll see you all next week.
All right, well, thank you, Jing, and I hope you all have a great week.
Yeah, thank you. And thank you, everyone. Yeah.